Today we're going to continue looking at lesson 2.6, which is combinations of functions and composition functions. So today we're going to form composite functions. We're going to determine the domain for these composite functions, and we're going to write functions as compositions. So what is a composite function? The composition of a function f with g is denoted by f and then a little circle followed by g. That's not a multiplication sign, okay? So it's an open circle bigger than a multiplication sign. And it's defined by the equation, and I say f of g of x, okay? So f is first, got our circle, g is second. So notice how because g is second, it is the function that is within the first letter f. So g of x is inside of the f of x function. So f of g of x. The domain for the composite function f of g of x is the set of all x such that x is in the domain of g and g of x is in the domain of f. So with that information, we are given two different functions. F of x equals 5x plus 6. G of x equals 2x squared minus x minus 1. We're going to find each of the following composite functions. We're going to do f of g of x first, and then we'll do g of f of x. So remember, when the f is first, that means the number that is second is the function that is going inside of the first one. So f of g of x. So that means that the f of x, which is 5x plus 6, I'm going to replace the x, and I'm going to put in the g of x function in its place. So we'll keep the 5, but now instead of x, I'm going to substitute in the g of x function. And then I have to finish the rest of the f of x function, so I'll have to add 6. So here's my f of g of x. Now I'm going to start distributing the 5, combining like terms. So we'll have a 10x squared, then we'll have minus 5x, minus 5 plus 6. Combining my like terms, we'll have 10x squared minus 5x plus 1. And here is my composition. So then if I want to do it the opposite way, because the g is first, we're going to do g of f of x. So the f of x function is going to go into all of the x's in the function of g. So in the function of g, there are 2 spots with an x. So we're going to be plugging 5x plus 6 in twice. So we'll have 2, and then we'll have 5 plus 6 in parentheses, quantity squared, minus, then in parentheses, we'll have 5x plus 6, and then we'll have minus 1. So we have to remember that if something is being squared, we are multiplying it by itself 2 times. I'm going to go ahead and distribute that negative. So we'll have a negative 5x minus 6. We'll still have minus 1. I'm going to multiply the binomials. 5x and 5x is 25x squared. 5x and 6 is a 30x. 6 times 5x is another 30x. 6 times 6 is 36. I'm also going to combine the negative 6 and the negative 1 at the end, so that gives me negative 7. I'm going to distribute the 2 to all of those, so we'll have a 50x squared plus 60x plus 60x plus 72 minus 5x minus 7. And now I can just start combining like terms. So the 50x squared will be as it is. I've got 3 x terms. I've got a 60, and a negative 5. So 60 and 60 is 120. Subtract 5 from it. We'll have a positive 115x. I have a 72 and a negative 7. So when I combine those, I get a positive 65. And there is this composition. Okay, let's look at a couple more. So here I have f of x equals negative 3x plus 1. G of x equals the square root of x. We're going to do our composition going both ways again. So remember, when f is first, we're doing f of g of x. So the g of x goes into the x in the f of x function. So we're going to have negative 3, but then now I'm replacing the x with the square root of x, and then I'm going to add 1. Well, there's no way for me to simplify that any further, so this would be that composition. If I go in the opposite direction, g of f of x. The f of x function goes in wherever I have an x in the g of x. So that means that underneath that square root, we'll have a negative 3x plus 1. Can't simplify that any further, so this is my composition going that way. So I'm going to have you guys pause the video. Here are two new functions. Go ahead and try the compositions in either direction. Okay, so for the first one, we should have gotten 2x squared minus 17x plus 47. And then in the second one, we should have gotten 2x squared minus x plus 7. All right, so now let's talk about excluding values from the domain of our composition f of g of x. So it says the following values must be excluded from the input x. So if x is not in the domain of g, it's not going to be in the domain of our composition f of x. So that's why it's crucial that we understand originally what is the domain for the g of x. And notice that it's the g because that's the function that is inside of the other function. So essentially, if things were written around, if I wanted to do g of f of x, well, then we're looking at the domain of f. So you're looking at the function that is inside the other function. We need to know what that domain is. Then any x for which g of x is not in the domain of f must not be in the domain of the composition. So that means that when we're doing the composition, we're looking at that domain, and that means that we've got to look at those restrictions as well. All right, so let's take a look at these two functions. We got f of x to equal 4 over x plus 2, and we have g of x to equal 1 over x. We're going to find the composition f of g of x, and then we're going to find the domain. So remember, f of g of x means that we are going to be substituting in the g of x function into the x in the f of x function. So we're going to keep the 4 on the top, but now instead of x, I'm going to have 1 over x, and then I'm going to add 2. So this is what we need to do. I don't want to see a fraction inside of a fraction. So because there's only one fraction within the overall big fraction, that is a denominator of x. I am going to want to clear away the fractions. So I'm essentially going to multiply both the top and the bottom of the f of x function by x. So everything on the top is going to get multiplied by that denominator of x, and then everything in the bottom is also going to get multiplied by x. So 4 times x is 4x. On the bottom, x times 1 over x is going to give us a 1, plus then x gets multiplied by 2, and that gives us a 2x. So now I no longer have a fraction inside of a fraction, and because I can't factor that denominator any further, there's nothing that I can simplify down any farther. This is my composition. All right, so to find the domain of this composition, there were two things that we have to look at. The first thing we have to look at is the domain of g of x, because that's the function that got substituted inside of the f of x. So the fact that my g of x is 1 over x, we are going to have a restriction. My domain cannot include 0, because the moment I plug in 0 into the g of x function, dividing by 0 is something that's undefined. So not only is that not in the domain of g of x, it's not going to be in the domain of our overall composition. The second thing we look at is then now we look at the domain of our f of g of x. Okay, so we're looking at this 4x all over 1 plus 2x. Okay, so I don't have to look at the domain of the original f of x. It's just what the function is that I substituted in, and then our new composition. So the fact that there is a denominator here means that I do not want that denominator to turn into 0. So I'd have to subtract 1, and I'd have to divide by 2. So I also, here, I'll put it over here. I also don't want x to equal -1/2. So every other number is going to work in our domain except for those two numbers. So my domain can go from -∞ up to -1/2, but I don't include it. So there's a parenthesis. Then on the right side of negative 1/2, we can go up to 0, but I can't include it, so another parenthesis. And then on the right side of 0, we can go up to positive infinity. So here is the domain of this composition. Let's take a look at another example. So we're given that f of x equals the square root of x and g of x equals x minus 2. So once again, we're going to find the composition f of g of x, which means that f of g of x, I'm plugging the g of x into the f of x function. So f of x is the square root of x, but now the x is going to be replaced with x minus 2. And there's something I can do to simplify that any further. This is my composition. So when we're talking domain, once again, because it was the g of x that I substituted in, I need to know what is the domain of g of x. So if we're looking at the fact that x minus 2 is a line, it's linear, there's no restrictions here. So far, if there's no restrictions on my g of x, that means that there's no restrictions on my domain for my composition function. But I can't just say that there's no restrictions. Now we have to look at the domain of our new composition. So the fact that we have a square root of x minus 2 means that I'm going to have some restrictions in this one. Because we never want negative numbers under the square root, but the first number that I can have is 0, x minus 2 is greater than or equal to 0. When I add 2, that tells us that x has to be greater than or equal to 2. So while there's no restrictions on the domain for g of x, there is for the overall composition. So that means that my domain is going to start at 2, and it's included, so it's a bracket. And if it's greater than, it's heading up towards positive infinity. So here's my domain of our composition. So I would like you guys to try this one. Here's my f of x and g of x. I want you to find the f of g of x composition and then find the domain of that composition. Okay, so notice that the 1 over x had to get substituted into the x in the bottom of that first expression, and then I multiplied the top and the bottom by x so I could get rid of the fraction within a fraction. And so that gave us 2x all over 1 plus 3x. So looking at the g of x, I know that I can't have 0 in my domain. And if I look at my composition, I set the 1 plus 3x equal to 0 and saw that the moment I have negative 1/3, that denominator turns to 0, so I cannot include that one either. All right, so now let's take a look at this picture. We're going to use the graphs of f and g to evaluate each composite function. So in this case, we're talking about f plus g. So that means I want f of negative 4 plus g of negative 4. We know how to evaluate f of negative 4. F of x is the blue graph. I go over to negative 4, and the blue point on that would be at negative 4, 2. So 2 is the first number for the f of negative 4. My purple is the g of x function, so I go over to negative 4, and it looks like that point is at 0. So I just need to add 2 plus 0, and so my answer would be 2. If I'm subtracting, since f is first, we'll have f of 0 minus, and then g of 0. So my blue function, if I'm at 0, it's 0, 2. Minus, if I'm looking at my g of x function at 0, we're down at negative 4. So 2 minus negative 4 is actually going to turn into a positive 6. When we multiply, we're taking f of 1 times g of 1. Well, f of 1. So if I go over to 1 on the blue graph, I'm going to be up at 3. The g of x function, when I look at 1, I'm down at negative 5. So multiply 3 and negative 5, and we get negative 15. And then when we're dividing, we're taking f of negative 3, and we're dividing by g of negative 3. So I'm going over to negative 3. On my blue graph, it looks like we're at 1. On the purple graph at -3, it looks like we are at -1. Well, 1 divided by -1 is -1. So now it's your turn. Take a look at these two pictures. On these graphs here, find adding at f plus g of 3, and then subtract at -3. We've got the product at 0, and we've got the quotient at -3. So you should have gotten these answers. When you added, you should have gotten -2. When you subtracted, you should have gotten 6. When you multiplied, you should have gotten -2. And when you divided, you should have gotten -1. All right, so now let's take a look at this example. It says find all values of x satisfying the given equations. So we are dealing with f of x to be 3x minus 1, g of x to be x squared plus 2x minus 10, and they're telling us that the composition equals 14. So we want to find x. Well, the last part here, this composition, because the g is second, that means that that is going to be substituted into the f of x function. So I'm going to start there. So this trinomial is going to be substituted into the x in the f of x function. So we'll have 3, and then we will have in parentheses x squared plus 2x minus 10. I'll finish the rest of the f of x function, so I'll subtract 1. And that composition, they're telling us that this equals 14. So now we have an equation where we can solve for x. I'm going to distribute the 3, so we'll have a 3x squared plus 6x minus 30 minus 1 equals 14. I'm going to start combining like terms, so we'll have 3x squared plus 6x minus 31. I'm going to subtract the 14 over to the other side, so it equals 0. Finish combining like terms. I am going to have 3x squared plus 6x minus 45 equals 0. Because it is a quadratic, we can solve by factoring. I see that they all have something in common. They all have a 3. So I'm going to factor out that GCF. That leaves us with x squared plus 2x minus 15 to equal 0. So I can continue to then factor what numbers multiplied in -15 but add to 2. That would be positive 5 and -3. If I'm solving for x, that means that I'm taking each of my factors that contain an x. Because that GCF of 3 does not, I can ignore that, and I can just set the x plus 5 equal to 0 and the x minus 3 equal to 0. Well, I'm going to subtract 5, and so that will give me a -5. I'm going to add 3, and that'll give me a positive 3. Here are my values of x that make that composition equal 14. So you guys try this one. I'm giving you two functions. I want the composition f of g of x equal -16. Find all the values of x. So once again, since g is the second number, or second letter, that g of x function, it gets substituted into the x in the f of x function. Then I set that equal to -16. So I distributed the -5, so I was very careful not to lose the negative sign. I combined all my like terms to one side, made it equal 0. I could factor, got two answers here, -1/2 and 1. So that's us using composite functions. We found domain of those composite functions, and we started writing functions as composite.